Hello guys, this video is represented by Ashwini Khandekar, Pratiksha Patil, Samruddhi Jatar, Ajinkya Gaikwad and Omkar Sarke. We are the student of Ashokra Mane Institute of Pharmaceutical Sciences and Research Savi. This video is guided by Mr. A. N. Dhagesa. In this video, we are going to see some previous year question and their solution. Question: explain non-linearity with method to determine non-linearity and cause of non-linearity. Non-linear pharmacokinetics, the rate process of drug ADME are depend upon carrier or enzymes that are substrate specific, have definite capacities and are susceptible to saturation at a high drug concentration. In such cases, as essentially first order kinetics transfer into a mixture of first order and zero order rate processes, and the pharmacokinetic parameters are changed with the size of the administered dose. Pharmacokinetics of such drug are said to be dose dependent. Causes of non-linearity. Non-linearity can occur in first, drug absorption; second, drug distribution; third, drug metabolism; fourth, drug excretion. Drug absorption. They have three causes. First one, solubility or dissolution of drug is rate limited. Example, Griseofulvin at high concentration in intestine. Second one, carrier-mediated transport system. Example, ascorbic acid. The saturation of transport system. Third one, presystemic gut wall or hepatic metabolism attains saturation. Example, Propranolol. The parameter affected will be FKA, Cmax and AUC. A decrease in this parameter is observed in former two causes and an increase in later causes. Drug distribution. At high doses, non-linearity due to two causes. First one, binding site on plasma protein gets saturated. Example, phenylbutazone. Second one, tissue binding site gets saturated. In both cases, there is increase in plasma drug concentration. The increase in VD only in first one causes. Third cause of non-linearity is a drug metabolism. The capacity limited metabolism due to enzyme or cofactor saturation. Example, phenylenediol. Second one, the enzyme induction. Example, carbamazepine. The saturation of binding site, inhibitory effect of the metabolite on enzyme, and pathological situation and change in hepatic blood flow. The last cause of non-linearity is a drug excretion. First one, the active tubular secretion. Example is a penicillin gel. Second one, the active tubular reabsorption. Example, glucose and water-soluble vitamin. The fourth, diuretics, change in urine pH and nephrotoxicity and saturation of binding sites. In the non-linearity show one equation is also known as Michaelis-Menten equation. The kinetic of capacity limited or susceptible processes is best described by Michaelis-Menten equation. The equations are shown as follows. Where first one, negative dc by dt is a rate of decline of drug concentration with time. Second one, Vmax is a theoretical maximum rate of the process, and last one is Km. Km is also known as Michaelis constant. When Km is equal to C, under this situation the equation is a negative dc by dt is equal to Vmax divided by 2. That is, the rate of process is equal to 1/2 its maximum rate. The graph is shown between the elimination rate dc by dt versus concentration. The graph is also shown in this video, where Km is greater than C. Here the equation shown is Km plus C is equal to Km, and the equation is reduced to negative dc by dt is equal to Vmax C divided by Km. The above equation is identical to the one that describes first order elimination of a drug, where Vmax divided by Km is equal to Km. This means that the drug concentration in the body that results from the usual dosage requirements of most drugs is well below the Km of the elimination process, with certain exceptions such as phenylenediol and alcohol. when Km is less than C. Under this equation, the equation show is Km plus C is equal to C, and the equation will become negative dC by dt is equal to Vmax. The above equation is identical to the one that describes a zero order process. That is, the rate process occurs at a constant rate Vmax and is independent of the drug concentration. Example, metabolism of ethanol of Km and Vmax. The parameter of capacity limited process like metabolism, renal tubular secretion, and biliary excretion can be easily defined by assuming one compartment kinetics for the drug and that elimination involve only a single capacity limited process. The parameter Km and Bmax can be assessed from the plasma concentration. The time data collected after IV bolus administration of a drug with the nonlinear elimination character. The rewriting equation is a negative dC by dt is equal to V max C divided by Km plus C. Integration of above equation followed by conversion is to log base 10. The equations are shown as follows. Semi-log plot of C versus T yield a curve with a terminal linear portion having slope negative Vmax divided by 2.303 km and when back extrapolated to time 0 gives V intestine. The equations are shown as follows. Graphs are shown as follows. At low plasma concentration, the above both equations are shown identical. The equating the two are simplifying further we get the equation. The Km can thus be obtained from the above equation. The Vmax can be computed by substituting the value of Km in the slope value. An alternative approach of estimating Vmax and Km is determining the rate of change of plasma drug concentration at different times and using the reciprocals of the equation. This equation is also shown in the video, where the Cmax is the plasma concentration as midpoint of the sampling interval. A double reciprocal plot or the Linear-Pharmacokinetics plot of 1 divided by dC by dt versus 1 divided by Cm of the above equation yield a straight line with the slope is a Km divided by Vmax and y-intercept is equal to 1 divided by Vmax. A disadvantage of above plot is that the points are clustered. More reliable plot in which the points are uniformly scattered. The equations are shown as follows. Is a dC by dt is equal to Vmax minus dC by dt Km divided by Cm. Thank you for